ואנחנו רוצים להתחיל את המושב השני שלנו עם הרצאה של פרופסור רון שער. פרופסור רון שער למד הנדסת חשמל בטכניון, קיבל תואר שני ושלישי בגיאולוגיה באוניברסיטה העברית, והשלים פוסט-דוקטורט במכון סקריפס לאוקיינוגרפיה בסן דייגו. מאז 2014 במכון למדעי כדור הארץ באוניברסיטה בירושלים.
In the Hebrew University, in the Institute of Earth Sciences, he studies magnetic fields of planet Earth and rocks, and Ron will give a lecture titled as follows: 200 years of research journey in order to understand Earth's magnetic field. Hello everybody. So I'm a geologist, and since I'm a geologist, I'm one of the Humboldt successors. However, his contribution to the field of magnetism was amazing. Let's start with some sort of a teaser, a little promo. You see these sort of headlines every so often. Headlines like Earth magnetic field should be worried about the magnetic poles, okay? Or the Earth magnetic poles will flip and destroy everything, you know, the future, whatever it may be. Forget global warming, worry about the magnetosphere. Earth magnetic field is collapsing and it could affect the climate and wipe out power grids. Or Earth's magnetic poles will flip and destroy everything. So you think about these global catastrophes, you don't really think about magnets. But again, this is called the map of doom. Okay, whether it's an atomic sort of holocaust or social media. Again, nothing is mentioned about magnetic fields. There is a geomagnetic storm though. So here you see, if you look at Wikipedia, natural disasters, there is no mention of those poles flipping or the geomagnetic storm. So is this something to be wary of? How is it connected to Humboldt? Can it cause a catastrophe? So I'm going to again talk about all these different phenomena, and von Humboldt will be the leitmotif. He will be what will connect between everything I mentioned. So let's begin with an overview, like a sort of a grocery list of geomagnetic discoveries that Humboldt discovered, without going into too much detail, just to understand what he did. And then we'll place this into a scientific sort of prism or field. We'll talk about, again, the magnetic field of Earth and so forth, what it does. And then from ancient Greece till our times and what discoveries were in this field of magnet fields. And then we'll talk about new discoveries, which is a unique research, again, archaeological, what we found about the magnetic fields from different studies. Okay, so let's move over to the slide and see there's a bit of some of this illustrations might be a bit distorted because I used an apple. But again, in his famous voyage between 1719 and 1804, you could see Humboldt down there at the bottom. He basically measured the direction of the magnetic field, but there is something that nobody did before him. It's to measure the intensity of the magnetic field. And once he did this, he discovered what was called sort of the magnetic equator. I will explain what that means. Number two, in 1806 and in Berlin, he measured a very quick change. Okay, this is here. This is a graph of a few hours, even less than an hour, the direction of the magnetic field. And at that time, if you remember, there was an aurora. There was that aurora storm, okay? Okay, that again, what you see in the North Pole in Northern Europe, that aurora, those lights, and he connected this to some sort of a magnetic storm, made that connection between magnetic fields, so he actually coined the term magnetic storm at the time. He also measured changes in the magnetic, again, fields also over time, not only in geography, and showed that the magnetic fields changes over time. And this is the direction of the magnetic field, and we'll talk about all these things in 1836 till 1850. You see some sort of a change of a few degrees. As you can see, actually measured this and showed it in a very orderly fashion. And the final thing, something that maybe seems to us to be pretty normal, or maybe the way in which we actually do science, he actually founded this global network of 20 measuring stations. It still work. Some of them still work till today. What do these stations do? They actually are synchronized among themselves. They calibrate the different tools they use, and they cover a global area. It's all calibrated between the years 1836 and 1841. This was a project, again, revolutionary of those stations, measuring station in Eurasia. So let me just again remind you of everything I said. First of all, okay, he discovered that sort of magnetic equator. There was a definition that he gave or coined the phrase magnetic storm. Then he understood that magnetic fields change not only in space but also in time, and again measuring the poles. And there was a global, again, sort of a network of those measuring stations all over the world. Okay, that was sort of like a grocery list. Now let's place it into scientific perspective, historical perspective, understand what a magnetic or geomagnetic field is. Okay, Earth has a magnetic field. Okay, all the planets have some sort of a magnetic field, or had a magnetic field, and then it sort of burnt itself out. And our planet's magnetic field is called geomagnetic, the geomagnetic field. You could basically maybe describe this field as some sort of a dipole. What does that mean, a dipole? That you can actually supposedly place in the center some sort of a bipolar sort of magnet in the middle. It's a little sort of, it inclines to one side. And that's our dipole. But again, our Earth is not a magnet. It doesn't really have a magnet. What creates the magnetic field is in fact this geodynamite, which is a whole complex system of these electric sort of flows and charges inside the core. Again, that actual core is 1,900 kilometers right inside. It's made of actual steel, and inside it's solid. Outside it's like a plasma, it's liquid, and when this material is sort of moves around, it creates a magnetic field. How does this material, how does it move around? How does it flow? It flows again in sort of like a cyclone, and these cyclones again are situated around that inner core. Those cyclones are like the spiral, this electric spiral that creates a magnetic field all around it, and that is how the magnetic field of Earth was created. But again, the true understanding of this, geodynamo works. It's one of the principles of physics, and Einstein actually defined the problem of understanding this geodynamo as one of the five biggest problems of modern physics. Today, we deal with this again. We deal with this question using a supercomputer. So what is it good for, this magnetic field? I think when people say magnetic field, the first thing that comes to mind is navigation, right? Because we use it for navigation. We use the compass, that directs us to the north, not pretty much. And bees use it, and bats use it, and seals use it, and they keep finding other animals or living organisms that use it or can feel that magnetic field and can use it for navigation. Not only big, again, organisms, but even types of bacteria that actually sort of grow all these magnetic crystals. And this chain is like a kind of the needle of a compass that directs the bacteria to swim to a place where there are more nutrients. There's actually a group in Caltech that performs different experiments to see if humans can also sense the magnetic field. The results are kind of 51%, 49%. We're not quite sure if maybe we can, yes or no. We have that ability to sense the magnetic field. Or maybe, again, this is a quality we had and we sort of wore into over time, maybe. Again, navigation is nothing. Without a magnetic field, we would not be able to be living on this planet, because the magnetic field that you can see here, basically those are the lines of Earth. It's not a symmetric picture because there's an interaction between the geomagnetic field and the other magnetic fields from the sun, and that is the magnetosphere that protects us, protects the atmosphere, and the biosphere, again, protects us from radiation, from all these charged particles and so forth. If we did not have this magnetic field, again, the sun would slowly peel off one molecule after another of our atmosphere. It would have deteriorated. Maybe that's what happened to Mars, by the way, our little brother Mars. Its geodynamo, or its dynamo, its Mars dynamo, extinguished itself long ago, and its atmosphere deteriorated because it doesn't have this mask, a sort of a shield, a screen. So again, I don't know, without this magnetic field, maybe radiation would have sort of demolished all living, all life, or maybe our life would have looked quite differently. So again, protection from radiation and from those charged particles. Okay, that is our magnetic field. So here is an illustration or a photo that shows sort of that sun wind. And when those particles, those charged particles, again, come again with great speed to the magnetic field, they actually deviated, they pushed aside, they do not penetrate Earth, except for a few particles that sort of get stuck in that screen around Earth. Part of those particles are able to penetrate. It happens near the poles, where the magnetic field, the geomagnetic, again, poles are sort of vertical to the surface of Earth, and where those particles do penetrate, we have those amazing fluorescent phenomena, the aurora, which is the interaction of charged particles with nitrogen and with oxygen, and again, we show ionized and disseminate light, which is an amazing phenomenon. The magnetic field, or geomagnetic, sorry, is pretty much stable, but once every so happened, it turns over. It's pretty dramatic. Let's say if we hold the compass 700 years ago, it wouldn't have pointed north, it would have pointed south. So once every so often, again, that polarity sort of switches around. Again, the magnetic north, again, becomes a southern, geographical south. Different, again, sometimes it can happen every 10,000 of years, as you can see here, even, again, millions of years. And again, we say our history is about 40 million. Okay, let's not go into disputes about that. You know why it happens that it's reversed? Because those spirals that we mentioned before in the geodynamo, sorry, are organized in such a fashion that one is a cyclone, one is the anticyclone. So they point in different directions. So then, right? And then this creates those two cyclones, it creates sort of a stable, right? A stable situation, because it's better to have one facing each way. And in any point of time, the anticyclone group becomes stronger than the group of the cyclones, and then sort of this weight is undermined, and then it switches around, it flips over. It happens every thousands of years or so. Okay, somebody asked a question, we just couldn't hear it, but he will talk about it soon. So the magnetic field, can I answer your question soon? If somebody asked if it affects something, we didn't make it out. Okay, so that magnetic field sort of flips over once in every so often. So let's once again say, okay, we said it's a dipole, again it's bipolar, sorry, it's a bipolar system. We said it protects the atmosphere and the biosphere from charged particles. The phenomena of that aurora are connected to the magnetic field, and the interaction, again, we said with the sun, and every so often it flips over or reverses itself. And then let me just say how it happens in praxis. It's not that magnet or that bipole sort of flips itself, but it weakens over time to a very low value. And part of our research, by the way, to understand, how weak it becomes, suddenly it recovers towards the other side. That is how that reversal happens. Remember that first slide? Again, where the magnetic field, again, weakens itself. This was mentioned in one of the headlines before, if you recall. So we gave you some sort of, again, a little introduction, a historical perspective. Now let's get to, again, the beginning of the 19th century, von Humboldt. So those ancient Greeks already knew those phenomena of, magnet fields. And Melatus already described a magnet. Aristotle also actually said that magnets have like a soul because it can attract things, it can pull things. Wow, that's magic. It must have some sort of a soul. And they knew, and they probably understood in the ancient world, this resource that's called this rock, which is a magnet, this natural magnet. What is that natural magnet? Some sort of a concentration of magnetite, which is a type of mineral, which was hit by a lightning bolt. It sort of charged it with electricity. So again, we get a very strong natural magnet, and of course chips, other magnet chips can stick to it. Now in Golan Heights, we have the site, it's called the palomagnetic sort of rock, if you know what I'm talking about. And again, this rock was struck by lightning. It has this this mineral magnetite in a high enough concentration that a lightning bolt would maybe affect a compass, and if we place a compass near this rock, the compass goes crazy. What else do I want to tell you about again in the magnetic field? Okay, compass, magnets always go together, right? In ancient China, 200 years again BC, they used compass not for navigation, but for sort of mystic purposes, to tell the future and such. You can see a reconstruction of a Chinese compass from the 2nd century before the Common Era, and you can see this is a spoon made of, which is a magnet. They sort of spinned the spoon, and then they saw where the spoon pointed, and then they, reached all sorts of conclusions. But there are also illustrations. You could see a fish which is a magnet fish made of some sort of steel, and then, swims around in water, and then it sort of flips to a certain side. And slowly the Chinese developed the compass as a navigation tool, because when it's cloudy, you can't use the stars. And in the 12th century, the compass arrived in Europe, and from the 14th century, it was used as a navigation tool. This is what the ancient compasses looked like. This is from about 1269 or so. You could see this is like a wet compass with that needle that can flip around, something that sort of floats on the water. And this is, again, a dry compass. It's on an axis of sorts, and it allows the needle to spin around. So the breakthrough, the scientific breakthrough with magnets, again, a book was published, The Magnet, written by William Gilbert in 1600. He was Queen Elizabeth I's personal physician, and what he did, he conducted this amazing experiment. He took like a ball, which was like the Earth, and he actually made it was a magnet, and to make it a uniform magnet, he sort of hit it all around, and then he brought close to the ball a needle that it was able to move on some sort of an axis. He brought the needle closer to that ball, magnetic ball, and saw where it was moving in on 3D, not just on a surface. And he saw that closer to the axis, the needle pointed downwards, and it was also vertical on this axis. And again, in relation to the surface, it changed in accordance to its location, and it was very similar to what navigators on the ocean saw as they basically sailed along the ocean. So when we talked about that bipole, he defined it, and he concluded that that Earth is a huge magnet. Now, today we know that Earth is not a huge magnet, and there's no sort of magnetic material that would be able to survive in the core of Earth. But at that time, it was a huge achievement. It's a very simple model. However, pretty quickly, those ancient navigators understood that the magnetic north, where that needle points, is not really doesn't overlap the geographical north, as Gilbert shows us. Because if we place that needle and we look at the place where that needle is pointing, and we measure the angle between the geographical north and the magnetic north, where actually there's some sort of, we calculate, it's called a declination sort of angle, which is that angle between the geographical north and the magnetic. This declination here in Israel is about 5 degrees. In Israel, the declination is more, depends where you're situated on the globe. And those sailors, those British sailors roaming around the Atlantic Ocean understood this declination, and you could see it over here. This is from 1697. They had this logbook. They had some sort of a record, that table to write the latitudinal line, the longitudinal line of Earth, so that they'll be able later on to develop, again, the compass for navigation. And in the year 1700, Edmund Halley, again, you know Halley, from the comet Halley, undertook voyages, again, to research the magnetic declination, and you could see his ship roaming all around, measuring and outlining the declination map, so that he could form, again, that map, the declination map of 1700, the magnetic declination map. That was the first magnetic declination map you can actually use for navigation and sort of correct that north. Now, till this day, they actually create these declination maps, and this is the first one is from 1700, but new maps keep coming out. The first out came in 2020, and last one, and they keep, you know, creating it. It's a mathematic, again, model. You can actually convert it, right? We'll have this, again, this model, again, on our phones or any navigation program. So this is from 2020 or 2021. It's good for the next 5 years or so. You could see the differences in declination, okay, declination. And there's another term I want to talk about is inclination, which is basically the tendency of the magnetic field, again, in relation to the horizon. So if I just put, again, here a compass that could spin all around, you can see that it basically points also not only upwards, but also downwards. So that angle is called the inclination angle. It's more difficult to measure it because I have to actually create some sort of a needle that would be affected only from the magnetic field and won't be impacted by gravitation. So mechanically speaking, it's a little harder to build this, but Humboldt was able to do this. But in the 18th century, they knew that there is that tendency. The magnetic field had this tendency, and it knew that it wasn't, again, a perfect bipole. Now we're with Humboldt, okay? So we can't hear the question coming from the audience. Again, if I stand in the northern pole and I'm holding a 3D compass, it's going to point downwards. And if I stand in the southern pole, it will point upwards, right, towards the magnetic field, yes. So if I stand here, latitude about 30, it will point, again, a little northwards and a little downwards, right? I'm talking about the Israel latitude line. Okay, so now we're talking about Humboldt. We finally reached Humboldt. So he knew there was changes in the declination, the inclination. So in his research voyage, he took a lot of measuring tools and a few additional tools. He took a declinatometer and inclinometer to measure inclination. So he measured both, and he did something else that nobody did. He actually measured the intensity of the magnetic field, and he did it in a very sophisticated manner. It was pretty smart. He took this needle right here, okay, in this inclinometer. Okay, he pointed it towards the magnetic field, and it gave it some sort of an angle, and it caused the needle to sort of roam around until it balanced out around, again, in the direction of the magnetic field. Now, the turnover time was proportional to the magnetic field, which is basically like a pendulum, right? Or other things, okay? It was proportional to gravity, right? So in this slide that you can't really see here, you actually see those points where he measured. Sorry that again, because I moved from a Macintosh to a PC, some of those pictures got distorted, but you can see the points where he measured the intensity of the magnetic field. He identified the place where the magnetic field was minimal, not zero, but minimal, and that is where he set again, that equator, so to speak, the magnetic equator. He was the first not to measure only inclination and declination, but also the intensity of the geomagnetic field. And he found sort of that equator where that intensity is at its lowest. So here's the Humboldt map from 1837. I basically outlined for you that red magnetic equator, again with some extrapolation to those different areas that he wasn't sure of. Not so far, by the way, from the accurate, magnetic equator, which is really phenomenal. But again, that insight that it was not uniform, it was an inspiration to Gauss against developments. And maybe we can talk about, again, a Gauss day, just like Humboldt day. And he also collaborated with Humboldt, by the way. And he also created some sort of a tool to measure the absolute, again, figures of the magnetic field and so forth. And the harmony of different spheres. Everybody remembers Gauss, by the way. You know, the units that we measure magnetic fields are called Gauss units, but Humboldt, I mean, what can we do? Nobody really remembers him. So people forget him, but although he actually, provided the initial steps for Gauss's work. He was the first who used the spherical harmonics to describe the magnetic field. I didn't say he developed them. Yes, it's one and the same, Gauss. Yes. Okay, that's why we have to hold such a conference about Humboldt. Absolutely. Okay, so we talk about the magnetic equator, one of his first discoveries that I mentioned at the beginning. The next thing I said was that Humboldt contributed to, again, the research of geomagnetic research, and he saw that it changes over time. Remember those measuring stations that measure the declination and the inclination of the magnetic fields, and with Gauss, the intensity as well. I showed you this slide, and in fact Humboldt actually sort of created a new area, paleomagnetism, which is basically what I do in life. So what do we know about this paleomagnetic sort of study? They basically measure the ancient magnetic field. We use measuring fields, those just like those that were founded by Humboldt. And why did I write 1832? Because that was the first year that they actually measured the intensity. Before that, they only measured the inclination and declination. From the 80s, we have satellites up in the space. Today, we also have the EU's, again, satellites that measure the the magnetic field using very high resolutions, almost to perfection. Before that, those direct measurements by people, by humans, we actually use, geological and archaeological materials that knew how to record the magnetic fields when they were formed, because every material that, again, heats and cools affects the magnetic field. We know how to read that information, and we can basically understand what was the direction and intensity of the magnetic field at the time this material was created, whether it's a rock or some sort of a mineral that was created even 3 billion years ago, or even a vessel, some sort of a stone vessel or earthenware from a few thousand years ago. So what do we learn from those paleomagnetic research? We can create such, again, clips to see how the intensity changes over time. You could say it's wonderful. Why am I showing it to you? Because 400 years ago, okay, I'm pointing to it now, there was an anomaly, this negative anomaly that formed, which was very intense, a sort of a pit in the magnetic field, and it grew and grew and grew. And there was this anomaly in the southern part of the Atlantic, okay, like a pit, you can call it, like a hole in the magnetic field. And we said, oh, what will happen? Will it suddenly disappear, as the BBC liked saying? I was saying no, this is not going to happen, because in a snapshot, this is what the Southern Atlantic anomaly looks like. It's like a hole. It already affects satellites. It affects their orbits, and the radiation is very strong, and it ruins the electronics and all sorts of flying vessels that fly over the area. They need better protection or better screening from radiation when they fly over the section, and it's growing. It's constantly growing. So the growth of this negative anomaly came at the same time, concurrently with the deterioration of the magnetic field. The intensity was becoming lower. So since the intensity was measured in 1832, first time they measured this, till this day, you could see the intensity is deteriorating, is diminishing, and we see it's going to hit low points at some point. So is this protective screen, will it really weaken? Is there some sort of a danger? I'm leaving this question open. I will answer it soon. This brings us to the next issue, magnetic storm, coined by him. He was the first, I said, that coined this term, magnetic storm, and understood that there is some sort of connection between Earth's magnetic field and that aurora from the northern pole. Let's just explain what, again, that sunstorm is or magnetic storm is. A storm happens when the sun starts emitting particles and radiation and magnetic field towards Earth. When this, again, radiation field and these particles and the magnetic fields, when they arrive in Earth's magnetic field, they sort of shock the field. There are these fluctuations. It shakes it up. And this basically enables sort of the drainage of charged particles into the atmosphere. Then you see auroras, not only in the northern hemisphere, but in all sorts of places around the world. And there's something else that happens when there is a magnetic storm. When those magnetic storms from the sun, when they hit the magnetosphere, okay, the magnetic field of Earth, and start shaking it up, we have in our atmosphere, we have these electromagnetic waves that are formed, that every such conductor, every such wave, again, it's like an antenna. I mean, what is that long conductor? Every line, every electrical line, every power line, every telephone line, it becomes like an antenna, intensifies those electromagnetic waves, and we get very high tension on the poles, on the edges of these power lines, these cables, and it basically burns, okay, all the transformers and the conductors or the receivers, whatever is there. So in 1806, again, he observed changes in the magnetic field, right? And he saw the aurora. In 1859, when he died, there was a great event, the biggest magnetic event that humanity knows about. That was like a mega storm. Now, what happened then? It was a few sort of telegraph cables burnt out. And they saw some auroras, by the way, in northern Africa and in the United States. And all the damage that, all the damage it did was, again, a few telegraph cables, again, burnt out. But next time it will happen, we'll be more exposed because our protective shield is weaker. We'll be exposed to, again, high power lines will burn out. I don't know what will happen. That is why we saw those headlines and the press wrote all those things. Where was it written? Okay, remember, power grids are wiped out. It's not that the magnetic field does it, but because the magnetic field is weakened and we have less protection against sunstorms or magnetic storms. Okay, so that is how we've just explained that first slide. Now, in the time that we have, let's give the Israeli perspective. How much time do I have? 7 minutes. Great. Okay, so in 5 minutes, I can do it in 5. So we have a lab, a paleomagnetic, again, lab at Hebrew U, where we take, again, archaeological and geological material, and we sort of take out information from there. So we go to volcanoes in the Golan Heights. There could be a whole conference about volcanoes in Humboldt. Again, different residue in the Dead Sea, drilling sites in the Mediterranean, in the Sea of Galilee. But you know what? They don't do this in Jerusalem. Many universities around the world do this. But there's something that you can't do in many places. But fortunately for us, we live here, again, on the margins of the Middle East. We can go to archaeological sites. We can collect materials that basically record considered the situation of the magnetic field at the time they were created, and we saw a few ancient sites there, John, Megiddo, Jerusalem, Lachish, Chatzor, Timnah, long list of archaeological sites all around Israel. Okay, and we collect all these ceramics and taboons and all these old sort of ovens and furnaces of sorts, and we collect all the material that we have, and we create some sort of a graph of the intensity, how the intensity of the magnetic field has changed over time. This is 1000 BCE, this is 1000 Common Era. We compare the magnetic field, and this, wow, we discovered so many interesting things about the magnetic field. At least the physics community knew nothing about it. We saw that about 3,000 years ago it was at its strongest. The magnetic field was the strongest ever, much stronger than we had thought previously. And we saw that the margins, the pulse of the changes, about 600 BCE, we saw great fluctuation, a lot of changes. And people didn't think that, again, such changes could, again, be present in the dynamo, in the geodynamo. Again, a few graphs here, but one interesting thing, using this graph as some sort of, dating. It's like that carbon-14 method for dating things, but it can be used for this purpose as well. Dr. Rachel and Yoav Vaknin, a week ago or 2 weeks ago, he was mentioned on the media, by the way, and again, he dated, destructions of Syria and Babylon and so forth, was able to date things back to that era, and I think we are conducting some sort of a study that can verify this at the moment, and I think that the biblical references to that pillar of fire, or, Ezekiel and what he saw, and he mentions electricity. Ezekiel mentions the word electricity. So I think maybe this, again, that space between Judah and Babylon when the Bible was written, the feasibility, again, because of the structure of the magnetic field and that anomaly that we are measuring, the prevalence of auroras was probably much higher, and that is why biblical figures were able to talk about electricity and pillars of fire. So again, Humboldt was the first to examine the magnetic field, and he measured it globally. He created stations. He identified changes in the magnetic field. He coined the term magnetic storm, and his measurement shows that intensity weakens over time. The Southern Atlantic anomaly, and some say this again shows that there will be again a reversal of the magnetic field, but no, we know it's not, because we know that from the astromagnetic research that things change but nothing really happened, and we see the geomagnetic again changes from materials that we studied shows us that the intensity has changed, and maybe Ezekiel and other prophets and biblical figures saw auroras. Thank you so much. Thank you. That was fascinating. So now we know that magnetic field is, so glad it's not going to, disappear, and it's not going to reverse. So great. Are there any questions?
Yes, Science published an article, I think, that we all read a while ago. There was an article several months back, maybe a year ago, that showed that these magnetic events, there was one large event 41,000 years ago. This led to the extinction of the Neanderthal man. When I read, by the way, the 50 pages, I didn't fully agree, and most of the geological revelations do not support the extinctions that occur because of magnetic fields. Conceptually, it makes sense when something reverses or weakens terribly, that we said radiation filters into the atmosphere, and biologists can tell you better than I can what happens, but there's no geological yet signs that show this indisputably. Does this impact climate? One of the reasons that we've been working so hard for 10 years to change the index in the 10,000 years, the last period, to see if there's a connection between climate and magnetic fields. There are such hypotheses that have to do also with protection of radiation, because the more that the magnetic field is weaker, there is more ions in the atmosphere, and the ions create a sort of nucleation effect, but this is yet to be thoroughly researched. It's one of the things we are researching, but talk to me in 5 years and I'll have an answer for you maybe. I'm sorry, I cannot hear the question from the audience. I can't explain that to you, but yes. There are events that we called magnetic spikes. Officially, they're called Levant magnetic spikes, because they happen here in Israel. Every time there's a spike, something happens in history. So I can't explain it to you, and what it has to do with political elections, I don't know. I really don't. Thank you. And Adir. I just want to make two small remarks. Initially, Ron talked about, when you asked the question, it mentioned animals that navigate by some magnetic sense. A small anecdote. We know that the Europeans that came to Australia were very successful, so to speak, by destroying, very cruelly, most of the Aborigines that lived there. But a couple remained, Aboriginals in various tribes, and there's one tribe that called Gugurimita. This tribe of Aborigines is about 700, 800 people, but a couple decades ago, a British scientist talked to one of the tribe's people, and while talking to that person, the tribesperson said, "Be aware, there's a poisonous spider to the north of your foot." To the north of your foot. That's a statement that made him very curious. And apparently, and this is for you, Ron, I don't know if you knew this, but apparently the Aborigines, or these tribespeople, they're born, they're with an innate sense of the north. It's not the geographic north, and it's not exactly the magnetic north, but they have a sense of the north, and everything they say, they don't say right or left. There's only suddenly, I don't know, a big shark appears on the west of my boat, or, you know, like the spider to the north of my foot. And Ron mentioned Gauss several times. Thankfully, when I read the great book, the only book in Hebrew that reviews Humboldt, The Invention of Nature, you should read that. It's amazing. It's fascinating. The number of places in which Humboldt, knows people in the world, not only world leaders, but also leaders in their field. He knew them personally. He met them. He encountered them. President Jefferson and the Russian Tsar and the King of Prussia, almost weekly for many years. And Darwin, by the way, took in his cabin the book of Humboldt's books when he went on his journeys, and Schiller and Emerson, the American, and so on and so forth, many famous names, and Gauss as well. Okay, so I would like to give you a small token. The first two volumes of Cosmos. I thank you very much for your contribution to the conference. You have expanded our knowledge and certainly enriched all of our lives and mine specifically. So this is on behalf of the Holon Technology Institute.